Hello everyone, welcome back to our video discussion. For today's laboratory activity 6, we're going to explore one of the most important concepts in signal processing, sampling and aliasing. This is our final topic, so I'll make everything clear, visual, and easy to understand. Let's begin. To start, we import our usual libraries, NumPy for computations and Matplotlib for plotting graphs. Then we generate a continuous time sine wave. In this example, our signal has a frequency of 5 Hz, which means it completes 5 cycles every second. We create a time axis from 0 to 1 second using 1000 points. That's a lot of samples, so the curve looks smooth just like a real continuous signals. When we plot it, we see a clean, smooth sine wave. Remember, this is the original signal we want to sample. So what is sampling? Sampling is the process of converting a continuous signal into a digital one by picking specific points along the time axis. Think of it like taking pictures of the signal at regular intervals. If we take enough pictures, we can reconstruct the original wave accurately. If we take too few, well, that's where aliasing happens, and that's exactly what we'll demonstrate. In our first case, we sampled at 50 Hz since our signal frequency is 5 Hz. The Nyquist theorem tells us that the sampling rate must be at least twice the signal frequency. In our case, 2 times 5 equals 10 Hz. So 50 Hz is way above that. That is the proper sampling. When we plot it, notice how the red sampling points follow the shape of the continuous wave almost perfectly. There is no distortion, no weird shapes, and no unexpected frequencies. That is what correct sampling looks like. Now let's lower the sampling rate to 6 Hz. Yes, it's higher than the signal frequency, but it's still below the required Nyquist rate of 10 Hz. This is called undersampling, and this is where aliasing occurs. When we plot our samples, look at what happens. The sample points create the illusion that the signal has much lower frequency than the original 5 Hz. This is fake. Slower signal is what we call the aliased signal. This is not real, it's just a result of sampling too slowly. This is why aliasing is dangerous in real-world systems. It can cause inaccurate measurements, distorted audio, and incorrect data interpretation. To wrap everything up, continuous signals are smooth, infinite signals like the sine wave we created. Sampling is capturing points from the continuous signals so computers can process it. High sampling rate above the Nyquist limits means we can faithfully reproduce the signal. Low sampling rate causes aliasing, which create false version of the signal with a lower frequency. Aliasing is one of the most common problems in digital signal processing, and this activity helps you visualize exactly how and why it happens. And that concludes our laboratory activity 6 on sampling and aliasing. I hope this visual demonstration helped you understand and concept clearly. Don't forget to like, share, and subscribe for more ECE-related learning videos. Once again, this is Cariel de la Cruz, BSECE3. Thank you for watching.